Hi everybody, hi, good evening, thanks for coming out. My name is Rich Ranky, this is my colleague Mark Sivak, and we have our third colleague and co-founder, Dinas Rodriguez, in the audience. I wanted to embarrass him, there we go. Hi, so we are 3Spark, we are a spin-out from Northeastern University, and we are very, very fortunate to currently also be one of the finalists here at Mass Challenge. So big, big thank you for Mass Challenge for letting us use the space for the event, and we would really love to talk to anyone about any venture, technical, hardware, software, our business about applying next year. We've had a fantastic time so far. We'd love to talk to you about applying next year. So this is the fourth member of our team. This is Donatello. He's the second version of the 3D printer that we're putting together, and he is what we're using to commercialize our technology. Our technology is 3D printing when we're able to embed conductive traces to make printed circuit boards, strain gauges, vibration sensors, force sensors, torsion sensors, thermal sensors within the body of a 3D printed structure. It's based on a RepRap or MakerBot style open source hardware and software with modifications built on top of that to the hardware and to the software as well. We have an XYZ platform to move around together the component, and we have two deposition heads, one for the plastic ABS or PLA based depending, and the second for the conductive material, which is a piezo-resistive elastomeric slurry that cools and hardens, that gives us the conductive effect. In the R&D cycle, the same way that 3D printing began in the first place, we're now adding to it by being able to integrate the electronics and the plastics together. So rather than having to buy a custom printed circuit board, send out for it, wait weeks, pay thousands of dollars for expedited shipping, you could build it right inside your part. And instead of spending the time to route wires, to screw on force sensors by hand, you can just plug it directly into a data acquisition or into your smartphone and other components around. For example, we have devices that we use in the R&D space. We're all mechatronics engineers from Northeastern, and we built lots of prototypes of very different projects over the last 5 years. In the Excelsior glove on the top left-hand corner, one example is being able to take all the electronics, the wires and sensors that are fragile and delicate, and embed them right inside the body of the structure, so we don't have to worry about it being broken off somewhere. In the lower left-hand corner, that's a printed circuit board with some extra microchips we had to apply by hand. It took almost half a day to solder the whole thing together. And although we're not trying to make integrated circuits or chips with this device, we are able to make the conductive choices, and that can save a lifetime. There's the three of us up there. You already know what we look like, so we don't have to spend too much time on this one. This is where the science came from. The sensor itself was a National Science Foundation funded project that we began 2.5 years ago. And the idea was that 3D printing is already used for so many different features and components, and it has this unique ability to build hollow voids and features. But what can we use that for? And the idea was that if we can embed a conductive material that's also elastic inside, then we can use this to measure mechanical changes, and we've also discovered we can also measure thermal changes with it too. In the top left-hand corner, that's an example using it injected inside a stereolithography material. Top right-hand corner, injected inside a fused deposition modeling material. And depending on what the packaging is around the sensing goop, the slurry that cures, you can measure all these different things. So once we finished the research for the sensor, we decided, okay, this is going really well, and the sensor works, but it has challenges in making it. So we need to find a better way of automating the fabrication. And that's when we came up with the idea of EELA. This is an embedded electronics layered assembly, and Donatello is the current model that we're working with. So we have our corner over in the green section, and we've been here now for a couple of weeks. We've had a great time Mass Challenge. We also had seed funding from Northeastern University, Center for Research Innovation, who's going through a Catalyst seed funding program that I'm happy to put anybody in touch with if you have connections to Northeastern as an alumni or as a current friend. And right now we're working in parallel to develop our business plan as well as complete our hardware. So, thank you. Any questions? We have a lot of friends here at Mass Challenge as well. This is Daniel. You should talk to him. That's a really interesting interface. So. Yeah. Okay. Hey, any questions, anybody?
What are the manufacturing tolerances of this machine, and how is that limiting the sort of end products that we're able to create right now?
Okay. Right now, we don't have first prototypes built with the machine, so we're not able to evaluate or characterize its performance as a complete system. When we were building the sensor, the the conductive material was limited by the size of the hollow tubes and cavities we could build, and how far you could inject it before the channel would prevent it from going any farther. So if you're looking at an SLA, then you can get down to 10 or 20 microns. If you're looking at an FDM, it's going to be roughly twice that. But at the moment right now, we're looking at the similar tolerances and resolution of commercial low-cost FDM system, like a ring.
Do you see this technology being more advanced to being the level of the object-type Connex printers, which actually shoots in multiple materials at once, so you can actually get a better structure?
Object actually gets really annoyed when people take silver ink and puts it through the nozzles, clogs them, and then calls them to go for a service contract because they don't want to be the ones to say, I'm sorry, you just messed up that $1 million system. Right now, the mechanics of the machine that we're using is not able to meet the same resolution as the Connex system. I think the multi-material for rapid prototyping is a fantastic application, and that's where we see this as well, because being able to go through prototypes smarter and quicker is the lowest barrier to entry. It's where all the maker community is thriving out of. We see all the hardware companies booming out of there too. And R&D labs for biotechnology, mechanics also need to have this easier and quicker way of building sensors into their devices.
Do you see this as really a possibility to generalize prototyping?
We're still exploring that. I think that...
Can you repeat the question?
So the question was whether this fabrication method could replace more traditional means of wet etching and dry etching, I guess, we're talking about prototyping printed circuit boards, standard or custom. For the scale of production, just like regular 3D printing, I don't think it can match large quantities, but for small batches and speed, I think this would be a great technology to look for if you can get it overnight or over the weekend rather than having to wait 8 weeks to get a custom board. And we're still working on the capabilities to match that as well.
Did I hear right? You said you're injecting the conductive material into the voids that are plastic rather than cold extrusion.
Right. Yeah, so the question was if we're injecting it inside the voids and cavities or if we're doing a co-extrusion methodology. Previously, when we did not have this machine, we were doing an injection method because we didn't have any way of reaching the intra-layer geometry. And now, because we have two deposition heads right next to each other, we can get inside the troughs and cavities right as they're being built, so we don't have any back pressure problems we had previously.
Did I hear you correctly? You're using a piezoelectric material as your conductor?
The question was what kind of conductive material we're using. Is it piezoelectric? We are using a piezoresistive, so we're treating it like a strain gauge or like a potentiometer you find on the analog volume. Okay, we have time for one last question.
What's the tallest structure you made going vertically with
The tallest structure we've made with this machine?
Yeah.
It's actually hasn't built the first structure yet. We have built very different structures out of the sensing material from when we're injecting it, when we're still completing the sensor research at Northeastern University. So I'll pass out some of these samples so you guys can have a look at what we've been, the different types of sensors and electronics we've built so far, and a little bit of show and tell so you can play with them when we go through the next presentations. Thank you very much, everybody.
Thank you.
Join Boston New Technology Meetup. Sponsor an event or venue. Present your idea and attend to network with Boston's brightest. Details are at www.bostonnewtech.org and in the video description.